Good evening, good afternoon, everyone. We're doing our stream today a little bit earlier after we've been away on a longer break. I've been a little busy with life in general. So, yeah, we've missed a couple of streams, but today we're finally back, as I said, about 2 hours early. Yeah, life's interfering again tomorrow, so I need to get up early. Anyways, last time we were here, we were looking at texturing and lighting. We've gotten our wonderful sphere textured with a very primitive stone texture. We've added a little bit of ambient lighting just so that it looks a little bit realistic. And that's pretty much where we're at right now. We've got this wonderful looking sphere that we can sort of move around, or we can move around it, and that's it. So today, what I want to do is I want to look at some sort of terrain generation, which means that we're going to be able to generate more than just a single, or render just more than a single chunk, which we have right now. And also I would like to be able to, sorry, lost my train of thought for a moment. I'd like to be able to actually try and generate some terrain using a noise function. And it looks like everything just crashed on me. Nope, it's back. So hopefully the stream survives that. Probably lost the OpenGL context here. Seems my graphics driver just died shortly and then came back, but luckily we're back. Just checking that the stream is also running. Yeah, it looks like the stream is running as well. Great. So what we are going to be doing, and I managed to do that a couple times. So what we need to do today is we need to make sure that we can render more than just a single chunk. We're going to hopefully get around to changing sort of the generation code here. Rather than just generating a sphere, we are going to try and generate some actual terrain. But before we do any of that, we need to sort of be able to move chunks around, so that right now, whenever we render a chunk, we're sort of using the same vertex buffer, and then just drawing elements from that. We need to be able to offset chunks relative to each other, so that if we have so that not every chunk just renders at 0, 0 in the world, so that we actually can see more than one chunk and they're not just all on top of each other. So the first thing for that is that a given chunk needs to sort of know where in the world it is. So what we're going to do is we are going to assign it x, y, apparently x, y, and z coordinates, which are going to be its location in the world. And we are going to take these as, these need to be signed, so we're just going to do integers. Might want to specify what size those are at some point. So what we're going to do is we are going to take these in as sort of normal parameters when we construct our containment class here. And then we are going to need a function here which will get these out. So we need to return the x, y, and z coordinates, and it would be kind of nice to get those as a vector of some sort. At least that's sort of my idea at this point. So question is, does GLM have anything nice for that? I'm thinking it might have something like an iVector 3, which I hope is a three-dimensional vector of integers. We'll find out. We'll call that get position. And it is, of course, const, doesn't change the contents of our chunk. So let's quickly go over here to our implementation. We want to say, take a look at our chunk, and the get position function we need to implement, and that will work simply by returning, and we'll see if this syntax works. The x, y, and z coordinates. Let's just quickly try and see if that compiles. Out of line. So nope, it has an implicit instantiation of undefined template, which is always my favorite. So what I'd like to do is I'd like to include clm/ivec, okay, vec3. Give that a go, see what happens. Yeah, that seems to be okay. Looks like this is a valid initialization of it, so that's great. Now our chunk now takes an int x, int y, and int z coordinates, and we initialize x from x, y from y, and z from z. And now we're of course getting errors when we create our chunk here, because we no longer have one at 0, 0, 0, or we need to tell it that this basic chunk here is at 0, 0, 0. So that now works. So what I'd like to do is I'd like to offset it along -y, because that's sort of away from us, so it should be easy to see. So I'd like this chunk to render at -1 chunk from where we are. Now to do that, we need to look at the chunk renderer. Now, currently the chunk renderer just binds the array buffer, and then it binds the vertex buffer, and then it sets up vertex, texture coordinates, and normal attributes, and then just binds the index buffer for this chunk, and then just calls the draw elements. So what we kind of need to do is we need to get these offset, but because the vertex data is in our vertex buffer, and we want to share that between chunks, we can't just write our global coordinates down into the vertex buffer. So what we need to do instead is we need to utilize a little bit of our vertex shader, because when we're outputting our position here, we have this normal transform or model transform, which we apply to our vertex. And doing this allows us to move stuff around on the screen. So that's sort of the idea of the model transform, is that it's supposed to be used to move things on the screen. So what we need to do is we actually need to affect this model transform while we're rendering. So what we want to do is we want to, and now I need to think a little bit, because that will be in the renderer code here. Because right now we're just setting a uniform matrix here, our model matrix, and our model matrix is just an identity transform right now. So what we want to do is essentially for every renderable, instead of just giving it vertex, normal, and texture coordinates, we also need to allow it to change the model transform. But because sometimes it's useful to sort of allow nesting of objects, it's also useful if it actually gets sort of a current model transform that it can then modify, rather than just building its own from scratch. So what we want to do here is we want to grab the uniform model transform here, and this is a GL int. We're going to call that model transform. We're going to initialize it like this. Yeah, we're going to keep it there. Now we want to sort of, as a fallback, just have it set so that it's this identity matrix, but we also want to pass it into the render function along with what the current model matrix is. So of course, this no longer sort of is what the renderer function expects. So it's going to get a GLint as well, which is the model transform and form. And then it is also going to get a, I have to check up on what the type of this is. It's a GLM matrix 4. There, the renderable. So we're going to take a reference to this constant reference as the current model transform. And we need to import the matrix. So there we go. With that done, we need to transfer this over to the chunk renderer as well, so that when it renders, it has these attributes as well. Now, we can sort of take two approaches here. Thing is, right now we're going in a loop here over every renderable and allowing it to change the model transform, and then we're not really resetting it in any way. So either we force a reset of the model transform every time through this loop, or we sort of require that every renderable sets the model transform on its own. And I'm sort of partial to the second option here, because that allows us to, for example, for the chunk renderer where we'll be setting it anyway, we'll skip one call to the GL uniform matrix because we won't do a reset, which we will then immediately overwrite. So we're going to require that every renderable sets up its model matrix. And this thing, we'll get to that in a moment. Right now, we're complaining that this render function doesn't match the one in our header file, so we are just, wrong button. We're just going to quickly grab these two parameters, switch over to the definition here, and we're going to add those as well, so that now it should match. Great. Yeah, not complaining anymore. Then we have the model transform, which I've managed to spell wrong, so model transform. False. And then we have our current model transform, which is not what we want here because we need to translate relative to that. So what we want to do is we want to create a map4d for matrix model transform. No, not model transform. We'll call it local model transform because it's local to our object, and we are going to be using that. And we need the value pointer, remember. So if we head over to, if I can remember where I copied this from, it's here. So for this was the GTC type pointer extension that we used to do that. So we're just going to include that as well, so that we get a nice amount of includes here. I would like that one up top. So hopefully that means they'll be able to find that in a moment. Now for the local model transform, what we want to do is we want to say GLM translate. I vaguely remember setting this up at some point. We've got code that does this in our camera. Yeah, GLM translate, like this. So what we're going to do is we are going to GLM translate, and we're going to take our current model transform. I just want to check if there's any sort of particular there. Matrix transform is probably what we're missing to get it to stop complaining. So we want to pull that in as well. So we have translate, and what we want to translate by is we want to translate by the chunk. So we have a chunk here, which we can call, we have a chunk, which we can call get position on, and we can multiply that by the chunk size, which will be chunk : size, so that it should switch over. And it's not a reference, we want to actually instantiate this variable. We set that into the model transform, and with any luck, we're actually good to go. So lots of fun stuff. So the GLM I vector cannot be multiplied within unsigned int here. So what are our options? So what it's complaining about is it wants to go with, on one hand, it wants to take the integer of the I vector as a parameter, and on the other side, it gets an unsigned integer, which is the size t here, and it can't really match those two together. So what we are going to do is that we are just going to static cast this to an actual integer, because it's non-negative and it's not too big, so that should be doable. And then we can't translate because it wants to use floats and we're giving it ints. So the question is, can we do something nice about that? Because the other option, which I think is what we're going to do with this, we're going to ignore that. We're going to go for the chunk here, and we're going to have it rather than, so our chunk code here, rather than returning an integer vector, it's just going to be a vector, and it's going to be the final position of that vector in the world. And yeah, it doesn't match this declaration, that's correct. So we are going to multiply it with size already here. Now this will of course give integers, but hopefully it will be able to transform that into floats automatically. There we go. So now we managed to link it, we get linked. So let's just quickly take a look at how that looks. And I'm seeing nothing, which is always the interesting result. So yeah, we're obviously doing something wrong here. Now the question is what? So we are going to start nice and simply here. We are going to take a look at the chunk render, and we are, rather than finding the local model transform, we're just going to do the current model transform, because this should be equivalent to the code we had a moment ago. So let's see what happens here. So we link it, we build it, and let's try running stuff. So if we do that, it works fine. So that's something. So the question then becomes, why doesn't it work when we're outputting using the local model transform? And of course, the easiest way to do that is to output a little bit of debugging information. So what we'd like to do is we'd like to get the chunk position. I have no recollection if GLM matrices and vertices actually are able to be printed in any sane fashion, but we'll find out. Otherwise, I might have to either define that or do some dumb code right now. Yeah, there's no sort of output for an output stream and a vector. So what we can do is we can do .x. So this is going to be the ugly way of doing it. So we're going to pull out X, Y, and Z here. See if that gives anything interesting. Oh yeah, still can't do that. Okay, so our Y coordinate is really, really bogus. That should not be that big. So we're doing something very, very wrong. I'm expecting something like -16, not oh wait, that's an integer overflow. Yeah, okay, fair enough. So my guess is when we're doing get position, it's going to calculate these as unsigned as opposed to signed. So we might want to consider just doing this as a normal integer rather than doing it unsigned. We're not going to get anywhere close to the range, and integer actually allows the compiler to do better optimization. So we're going to switch to that. So let's, and again I forgot. So what we've done here is that what's happening is over in our chunk code here, when we're doing this, we have -1 times an unsigned integer. So what it does is it says, okay, well, this is an integer. It becomes an unsigned integer, which drops the -1 and makes it like 4 billion, essentially. And then it multiplies that by the unsigned integer. At least this is my guess at this point, which makes it a little bit less, but still around 4 billion, and then it converts it to float. So what we're doing is we're making this a signed integer by changing the definition over here. And by making it a signed integer, the expression should stay signed, and we should get -16. So we're going to try that. So that gives -16. So let's go back and get the correct transform matrix again. So we are using the current model transform. We want to grab the local model transform instead, and we want to render, or rather compile that. And now that that's compiled, let's switch over. And it's below us because I forgot that Y is up down, not left right. I meant -1 on Z, but it works, essentially. So now we have actual code that will allow us to render more than one chunk. We can just add more than one chunk to our list of, well, chunks. This is sounding really weird. And then we can just pass more than one chunk to our renderer, hopefully. We can just quickly try and set that up so that we should be rendering more than one sphere. So right now we're just creating a stupid amount of, or just this stupid list here with chunk, and then we pass to our renderer that we want it to render this one renderable, which is based on creating, and I think, yeah, apparently my machine's a little bit dodgy today, which is based on creating this renderable from our chunk renderer. And we're actually doing that in the main loop, which is not ideal, but, well, this thing, yeah, it stores the renderers for every chunk, so that's not too bad. We're not doing a massive amount of computation every time, we're just doing lookups. So that's doable. So ideally, if we just do it sort of the really simple way, I want to, yeah, we'll just keep this at like -1 and then create one at 1. Call it C2. Just to have them. In a moment, we're going to sort of expand and make bigger areas. And then I should be able to create another renderable R2 from C2 and have the renderer render R2 as well. At least that's sort of the idea. It's built, which is always a good first step. So if everything goes well, we've got one below us and we've got one above us. So we're now actually rendering two separate chunks. And we're outputting a lot of data about the chunk positions, which I'm going to pull out in a moment, because that's a little slightly annoying. So we've got this chunk renderer, we've got our debug line here, which we want to kill off. Great. So what we want to do is we want to create a set of chunks sort of around the player. I think we're going to focus in the X and Z orientation at first. And then for every one of those, we need to grab a renderable and get those rendered. So rather than having just a single chunk, we're going to have a vector of chunks that we're going to be running with here. And then I want to save that for a moment. Then I would like to, for CS to be a standard make unique at some point we're going to encapsulate this within the concept of a world. Maybe today, maybe not today, we'll find out. But I definitely want to create a vector of chunks like that. And then we are just going to go for we're going to have a constant expression here. A radius of like 8. So we're going to have x be minus radius as long as x is less than or equal to radius. We're going to add to x. And then we're going to do the same for z. There we go. And then for our chunks, we want to push a new chunk on this. We are going to have actually we can use the in place back so that it creates it in place. And this is going to be x, 0, z. So that should create a massive amount of chunks. Now we've got our renderables up here, which aren't really working that well right now. So what we'd like to do is essentially we'd like to go for, we're going to do it nice and simple up here. We are going to create a standard vector of GLES renderables. This is going to be our render list. Stuff we want to render. Then we are going to go for we're just going to go const auto for every chunk in our chunk list. We need to dereference because it's a unique pointer. We are going to ask the renderer to create a chunk renderer for us. And then we are going to push that onto our render list. Render list push back. We don't need to do that. So that creates a render list of all those chunks. And if we put that render list for rendering, that should ideally work. I've forgotten to put a type on the radius. It's an integer. There we go. Linking and done. Let's head over here, refresh. And we are using more memory than Emscripten gives us. So, given that, we are going to switch back. It allows us to use 16 megabytes of RAM. We are definitely going to be using more than that. So what I'd like to do is I'd like to go over here and say, along with the linker flex, I believe, we want to say S total memory is, and this is where it becomes interesting. I want something along the lines of 2 to the, I think, 30th. That'll give us a gig of RAM to work with. Probably not ideal in the long run, but it's something to start with. So let's try and see if that compiles. We're linking. And then we are going to head over here, refresh, and see what happens. There we go. So let's head out. We should see more spheres. Yeah, we have spheres en masse in every direction, hopefully. So now we are essentially rendering a rather weird looking world. So what we want to do now is we want to give it a little bit of Yeah, well, essentially a little bit of texture or surface area